Great, thanks a lot. Thank you so much. I'm so thrilled to be here. I really appreciate that you brought the Michigan weather for me here so I could feel right at home today. And thank you all for coming. So I'd like to talk to you today about our experimental characterization, constitutive modeling, and computational simulations of the soft tissues of the knee. I'm going to focus on the anterior cruciate ligament today. And so to start off, since you might not all be familiar with knee structure, this is a computational model, and I'm going to add tissues in and explain what they are. So we're starting with the femur and tibia, okay, and okay. So first to come in will be the anterior cruciate ligament, or ACL, in the center of the knee, and then the PCL, cartilage on the tibia and femur, the menisci there in red and blue, and then the medial and lateral collateral ligaments, okay, and finally the patella and patellar cartilage, okay. So this is a computational model that comes from an MRI that we then segment and find all of those tissues. So as I said, the anterior cruciate ligament, or ACL, is the one in the center of the knee, and it's a complex tissue structure. So it's comprised of essentially two main regions or bundles, the anterior medial and the posterior lateral, or AM and PL bundles. These are, collagenous tissues that insert directly into the bone. They have complicated insertion geometries, or entheses. They're not uniform. They're composite materials. And mechanically, these are tissues that are nonlinear, anisotropic, and also viscoelastic. And there's no physiologically relevant configuration in which the anterior cruciate ligament is completely unloaded. So some part of it is always carrying some amount of pre-strain at any natural knee flexion angle, right? So the PL bundle is twisted about its own axis, and the AM bundle wraps around that, okay? And so just to give you an idea of, so taking one of these bundles, the AM bundle in this case, and untwisting it and just doing an MRI of that, I've just kind of cartooned in what these insertion sites look like. They're not regular. They're complicated shape-wise. And the cross-section is also, irregular. You can see sort of the individual collagen fascicles that make up the highest hierarchical structure of the collagen in a ligament. Okay, so when you tear your ACL and you want to return to high-level physical activity, you have to have it surgically replaced. The gold standards are patellar tendon autografts or allografts, also hamstrings tendons, autografts and allografts. And outcomes can generally be good, but there are limitations with these procedures. And so I've listed several of them here. Whether you have an autograft or an allograft, there are some limitations. And with allografts, for instance, the population that has the highest incidence of ACL tears currently and the highest rate of increase of ACL tears is girls, 14 to 17. And in that population, autografts are not a great solution because of risk of damaging the growth plate during the surgery. So an allograft, which comes from a cadaver, is often the preferred solution, and they fail at an unacceptably high rate. Now, when you tear your ACL, you also have a much higher rate of developing osteoarthritis within a decade. Okay, and living with that for, if you're 15 years old when you tear your ACL, you develop OA a decade later, now you've got 35 years before you're a candidate for full knee replacement. Okay. So trying to prevent these injuries in the first place would be awesome, right? But also, there are problems with these graphs include unmatched biomechanics. I'm trying to illustrate here. So these are stress versus strain curves of an anterior cruciate ligament in blue and a patellar tendon in red. So the patellar tendon being the tissue that's often used to replace the ACL. You see the nonlinearity, you see viscoelasticity in the response, and you see also that the patellar tendon is not a good biomechanical match for the ACL. It's much stiffer, right? And it's hypothesized that that is one of the factors that leads to this early incidence of osteoarthritis. And so what I've been interested in doing for the last several years is to characterize the response of the ACL, develop constitutive models for it, and as I said, it's nonlinear, anisotropic, heterogeneous, viscoelastic, and these models have to be suitable for use in a computational framework that would then allow us to implement them into computational studies of the knee during impact or gait analysis to assess injury risks and potentially, down the line, prevent the injuries in the first place. And I have that sort of in parentheses because I won't get to too much of this in the talk today. And then previously, we've done a lot of work in tissue engineering to build a replacement graft that can restore native function and eliminate this unmatched biomechanics. But so, sorry, I got a lot of bullet slides up front here. So when you test soft tissue, you have two options. You can use human tissue that has been frozen, it's cadaveric tissue, or an animal model. So the animal model has to be justified, and sometimes there aren't good models, but in the case of the ACL, there is a good animal model, the sheep. We have this history of variability, so you have to test several specimens to get a good read on what is the actual mechanics of the thing you're investigating. And we want to, limit the number of animals we use and the cost of doing these experiments. So it would be great to do multiple tests on every sample that you get, but tissue properties are changing. You have to keep the tissue hydrated and cool. If it was, a fresh sheep leg a couple hours ago, it's slowly dying during the experimental window. And it's viscoelastic, so you have memory of previous excursions. These are all things you have to worry about when trying to design tests. And also, you don't have the luxury of ASTM standards, right? You've got what the tissue's giving you in terms of geometry, shape, and size. And that's often not conducive to being able to test an anisotropic material in multiple states of deformation, which you would need to do normally to characterize that anisotropy. So what's available to you is somewhat limited. And directly gripping soft tissue is a nightmare. It's a mess. It's really soft. It tears. Localization at the grips, tearing at the grips, slipping out of the grips are all issues we have to deal with. So we've been exploring the use of full field methods to be able to characterize these tissues with a limited set of experiments. And in the case of the ACL, leave the bones attached, grip the bones, and do the measurements from there. Keeping those native boundary conditions. So the native boundary condition being the enthesis, or insertion into the bone, because that's often where failures may be occurring too. And we can examine the whole response. So I know this is mechanical and aerospace engineering, so I always like to warn, I'm a mechanical engineer, but I like to warn you that when the blood, guts, and gore are coming, so here comes the blood, guts, and gore. Here's an ACL, here's a knee, taking everything else away so you can see the ACL, you see the two bundles, you see the twist, you see the pre-strain in there. And so trying to characterize something that is clearly not in its natural configuration is fraught with problems also, right? So you want to start from a natural configuration. In this case, we untwist, okay? And don't worry, the animal's long gone. And then we cut the tibia in half and separate the two tissues. They just kind of rip apart. And so we could take each of these bundles individually and test them. And you see when we untwist, the AM bundle's longer than the PL bundle, right? So again, even in this untwisted configuration, you can't find an orientation in which both bundles are simultaneously unloaded. So we split them up and test them individually. Okay. So we use digital image correlation for the first set of data I'm going to show you. Again, here's a nice MR image of one of the bundles. So there it is mounted in the load frame. We have two high-speed cameras to do 3D DIC. And then we had to stick in a third camera at 90 degrees to get the profile or the third direction. Now, when traditionally investigators do an experiment like this in which you're pulling on it, measuring the displacement grip to grip, and you have a load cell in there to measure the load, convert the load to stress, convert the grip to grip displacement to strain or stretch. It's not uncommon in the biomechanics literature to see results like this. 8 separate knees, 8 different stress strain curves, okay? So this is nominal stress versus stretch. And so this is why we implemented digital image correlation, right? So it's a method that's been developed for metals and engineered materials. And there's a lot of developmental work one has to do to get it to work well for tissue, but it can and it does. And so the idea is to put a speckle pattern on the tissue. You need a random speckle. It's actually more dense than this, but this is deliberate to show you there are dark dots on a light surface. And as you do an experiment, that whole deformation field of the surface is captured with the cameras. And you convert that into displacement fields and then strain fields, okay? So from that, you're measuring strain directly on the tissue surface, okay? So we did this experiment, and I'll show you. So once you post-process and you have the displacement fields and then the strain fields, you can convert them into color-coded strain contours, okay? So as I pull on this, we'll see this. The colors change as the strain increases. So I'm going to give you the normal strain in the axial direction here. So blue is unloaded, positive strains are going that way, right? So we do the experiment, and you see fairly homogeneous loading, strains up to only a couple %, not completely homogeneous, but reasonably homogeneous, right? Strain fields as we load and unload. Okay, but this also gives you the transverse strain fields as well, okay? So I'm going to do this same experiment. Now we're looking at the strain fields in this direction. And now unloaded is this color, right? And positive strains are yellow, red, and green. And so we do the experiment. We're pulling on it this way. And what's happening? When you pull on something this way, it should be doing this, and this is doing this, okay? And so Caitlin Mallet brought me this, and I said, okay, well, that's wrong. But it actually isn't. So if you look very closely, clearly this tissue is expanding laterally in that direction. That's why we put another camera on to see what was going on in this direction, and it's contracting in that direction. So overall, the volume change is a little too noisy to really pin down. It looks like there is a volume change, that it is a positive volume change. but not something like what this would suggest. This is happening because the fascicles in the mid-substance here are nice and round like this, but as they insert into the bone, they flatten out, and all of the fascicles are kind of splayed. So they're splayed there, and then they come down into the mid-substance nice and round, and then they splay back out going into the tibia. So when you pull something like that, those mid-substance fascicles are going to flatten out, and that's what we see there. So they spread this way and compress that way. But using this DIC data and just converting the tissue level vertical contour information into strains, okay, we go from this, what we saw grip to grip, for the same 8 experiments, to this. Okay? So this subject-to-subject variability that we've been led to believe we have to live with may not actually be a thing, right? Measuring at the tissue level, we get much more repeatable results. We also see that the tissue is stiffer than previously thought and often reported. And this hysteresis at this strain rate is really not a big deal either. So the viscoelasticity may not be as big a deal as the nonlinearity. But as a person who wants to now develop a mathematical model or a constitutive model of this, I can't do anything with this, right? What am I going to do with this, right? And what's normally done is all of that's averaged, and some sort of average response is reported, and that's what people try to model. But if this were real, that's a useless approach, right? Because you might have an average ligament, you might be an outlier, and I might be an outlier on the other side, if that's real, right? But if this is real, okay, now we have something deterministic, okay? All right, so now you say, okay, well, I did a uniaxial test. I can take a constitutive model and fit it to a uniaxial tension response. Well, are we capturing the uniaxial tension response? Probably not. Why? Well, we know from mechanics, if you have an isotropic material and your aspect ratio of your specimen, so length to width, is about 1, you're testing in plane strain. So you have to go out to an aspect ratio of something like 4 to actually get a uniaxial tension response. In an anisotropic material, you've got to go out much, much higher. Okay? So the AM bundle I showed you had an aspect ratio of around 3 or so. This is some patellar tendon data. And you see that as I change the aspect ratio of the specimen, and I'm pulling sideways, as it gets longer, I'm transitioning from plane strain towards uniaxial tension, but I'm probably still not there yet. Okay? So how are you going to fit this to a mathematical model is the next question. I'll come back to that in a minute, but what we did next, and I was prompted like a couple years in a row talking about these results at conferences. Someone would stand up, and it was the same guy. His name's Mike. He'd stand up and he'd say, okay, well, Ellen, is this measuring the full volume or just the surface? And I say, well, you know, Mike, it's just the surface. So I said, okay, damn it. Let's figure out how to get full volume information. Okay, so we've now developed this in situ MRI loading device that gives us full volume displacement field. So this is the AM bundle in the chamber, in the load chamber. The whole thing goes inside the MR. And we were able, in our first set of data here, we were able to get about 3 slices through the thickness here. And so as you pull on the tissue, the phase angle of the processing protons changes, and it's encoded directly with the amount of the local displacement field. So by measuring that phase angle change, you're getting the local displacement field, and we get it throughout the volume. And so there again, we can convert to to strain fields. So just showing you, we were really only able to get 3 good slices through there. And I also want to show you, again, how the cross-sectional area changes as you move down the ligament, right? It's not a nice uniform tissue. But what we're able to get from a given slice, slice 1, 2, 3, these are the longitudinal displacement contours as a function of the load in the columns here. And it's perhaps best to look over here where the load is the highest. We fixed the top and pulled the bottom down, and down we said was positive. So this is positive displacement, right? And this is essentially near 0 displacement. So we're getting that displacement field in the vertical direction as a function of load in all of these slices. And we can also get transverse again, and the third direction too, okay, through the thickness, what's happening in this direction, right? So we have all of that displacement information. You see the, lack of complete homogeneity there, but you can convert those into strain contours. This is the vertical strain contour again, horizontal and through the thickness. Okay. And so then if what you can do is, again, take all of this information at the tissue level, average it, get an average strain, and plot, again, a stress-strain curve, right? And so we did this for 6 knees, and we got stress versus stretch, 6 different sets of experiments here. And I plotted them like that because I'm going to now overlay them on what we saw with DIC, okay? So 2 different techniques. One's surface, one's volume, one's in air, one's in water. Similar results here, right? And so we're very excited about that. But, I know what you're probably thinking. You're thinking, well, congratulations, Ellen, you just made the world's most expensive strain gauge extensometer. And yes. Yes, we did. But now the challenge is to take all of that data and do more with it, right? So let me summarize the experiments just really quickly. So I showed you the AM bundle results. We did the same thing for the PL bundle too, using DIC and MRI to measure displacement fields, and that they match up quite well. Both techniques reduce this specimen-to-specimen variability in soft tissue, or what I like to call experimental uncertainty, right? The whole idea is if you are measuring a material property, you're measuring a material property. If you're making a measurement and a material property is changing every time you measure it, you're not measuring a material property, okay? So we saw, among other things, that the bundles are stiffer and less lossy than previously reported. And although I didn't show you the data, we saw the same thing for the PL bundle. Yeah?
Go back 2 slides. When you look at the higher stress ranges, are you able to?
So we weren't able to with our first setup. Good question. So with the MRI setup, we were only able to go to 150 newtons or something of force. So we've redesigned. We've got stiffer load cell, or stiffer load frame, higher load cell, and we're in the process of refining everything we've done to get even more accuracy and get up to higher loads. Yeah. Okay, so now we have these data. How do we model it? Okay. We have a couple different approaches here. One approach is to say, okay, I'm literally going to model this thing as a composite. This is the bundle. This is what it looks like. It's got fascicles of collagen with matrix in between them, right? And so put those together, and then matrix all around it. Moreover, a fascicle is a combination of fibrils. And those fibrils also have some matrix in between them, Those fibrils are combinations of fibers, and those fibers are combinations of individual collagen molecules. Well, okay, finite elements, we can't get 4 orders of magnitude of hierarchy in our finite element model, but we can get 2. So we could model the collagen fascicles and fibrils as anisotropic nonlinear materials, and model the matrix as sort of an isotropic material. And so we like to use models that are physiologically related to what we're trying to explore here. So to model a collagen fibril, we used, in this case, the Macintosh chain model. So this is a nonlinear chain model, and it describes the nonlinear force versus length relationship of a relatively stiff molecule that's almost fully stretched out, and then you finish stretching it. That's unlike some other kinds of rubber elasticity models where you're starting with something like this, and you stretch it way, way out. Okay? So we're starting with molecules that are almost fully stretched out and finishing that stretch. Okay? The model parameters are things that you could, at least in theory, relate to the actual structure. So the mechanical response of a ligament is largely due to collagen. There's also elastin in there. And you can see that from the staining, what the collagen looks like almost fully extended chains. And so you can describe how stiff those chains are via this persistence length parameter, what the fully extended length is, or contour length, and where you're starting from. And as you change some of those parameters, like the ratio of the stiffness to the contour length, you get different stress-strain curves, right? But you get that nonlinearity that we see in the actual data. We take that one chain model and make it 3D now because we're trying to describe three-dimensional deformation. So this is the strain energy density function when we take 8 of those chains and put them in an anisotropic unit cell and add up the strain energy. Again, the parameters are the same things we talked about before, but now because it's a network, you have a rubbery modulus, sort of a network stiffness. And mostly for computational purposes, you want some volume change, so we put a bulk modulus in there instead of making it incompressible. So that's our fiber model. Then for the matrix, we just described it as neo-Hookean with, again, a modulus term and a compressibility term. Okay. So putting all that together now, we would simulate the experiment that we did, so pulling on the bones the same way we did in the experiment, and compare the contours that we got with the experimental contours. So the vertical displacement contours, experimentally and computationally, matching up very, very nicely, and the horizontal contours, right? Again, capturing this widening of the tissue. And we can convert those into strain, and we see we don't get full homogeneous response. We get the transverse positive strains, and we even get shear. I didn't show you the shear earlier, but this is not homogeneous loading. So we see shear in there. And again, you can take this information, get an average strain, and plot a stress-strain curve, and plot it against the experimental stress-strain curve, and predict the response pretty nicely. So are we done with this? Well, no. It turns out if I took a different model, I could capture this axial response equally well, and then if I simulated shear, I would get something completely different. And so we did that. We took 3 different models the one I just described and one from the literature. The one I just described, I can independently vary the shear stiffness from the axial response. And the one from the literature is an anisotropic model of Hosopfel, Gasser, and Ogden. Fit those equally well to the axial data. Okay. Also, in some cases, we have a little bit of transverse data. So instead of pulling normal or parallel to the fibers, turn the tissue sideways and pull on it that way, get some transverse data. We could fit these models equally well to the axial and transverse data, and then just simulate shear, and we get completely different responses. So which one's right? Right? We don't know. So one way to, I guess, to get at that is to go back and see how well we capture the magnitude of our shear contours with these different models. But we were also interested in potentially trying to measure the shear response directly. This is about as close to a nightmare as you can get in the lab. So here's what the student's first attempt. This is what he hoped was his undeformed configuration, and his undeformed configuration already has some shear in it. But I'll run through it so you can see how the contours develop as you shear it, and then you get great localization and tearing again at the grips, right? So we're working on refining this set of experiments to try to get good shear data to figure out which of these different anisotropic models is really capturing the response of these tissues. And if the answer is none, we got to come up with one that does. Okay, but another way we can go about using these data is with this virtual fields method of characterization. So this comes from the principle of virtual work, right? The weak form of the statement of equilibrium. And it's a balance of the internal work and the external work. In this case, written as a cost function. So pi is the stress, the pk stress, first Piola-Kirchhoff stress. U star, capital U star, is the virtual displacement field. So you have the internal work and the work of the external tractions there. Okay. So the stress depends on the strain energy function. The strain energy function, in turn, is a function of the displacements and other material parameters. And in this case, for an anisotropic material, you could put in the local fiber direction as one property. And then you have those constitutive properties from a couple of slides ago. Let me just jump back here. These kind of properties, right? The material level properties. They're sitting there in this vector, okay? Because we're talking about nonlinear tissues, highly nonlinear tissues, we can't solve the virtual work as a series of linear equations. That's why we converted into a cost function, and we're going to just try to find that set of parameters that minimizes this cost function, okay, numerically. So from the MR data, we have the actual displacement fields. We can see from MRI the local orientation of the fibers, and the virtual fields method has us come up with plausible, compatible displacement fields that are U star in the cost function here. So we decided to look at this HGO model that I mentioned previously. It's essentially a model of nonlinear fibers in a nonlinear matrix. Okay? The fibers, again, are are, okay, so this is the matrix term here. It's again just essentially neo-Hookean matrix with one parameter. And all of this, and this is the compressibility, and all of this is the anisotropic fiber model, okay? We have a parameter describing essentially the initial stiffness of the fibers, a parameter describing sort of the nonlinearity of the fiber response, another parameter describing the local orientation distribution function of the fibers. So if I'm looking at a region, even though the predominant fiber direction is this way, how dispersed is that? That's kappa. And then we have the prominent fiber direction. Okay. So my really brilliant student, Callan, who also suffers from imposter syndrome, said, I'm going to do this. And what I'm hoping happens is if I compare the AM bundle, in which the collagen looks very organized everywhere, and the PL bundle, in which it looks more disorganized everywhere, since these are both ligaments, they're both comprised of collagen, I should get the same material properties everywhere except this kappa property, because that's the one that's describing the dispersion, and that's the only thing I see that's different. So she said she's going to try this, and she said, and watch, it won't work. That's the imposter syndrome she has. Well, it worked. So none of these parameters for the AM bundle or PL bundle are significantly different except for kappa. A low value of kappa means things are well aligned. A higher value means they're more distributed, and that's what she found, right? So we're doing a lot more with this work. As I said, we're refining the experiments. We want to get more data, more slices, larger loads, a lot more data. And we want to explore different models with this virtual fields approach to try to find the best one overall to describe these bundles. And when we do that, then we're ready to put it back into our computational model and start looking at gate models and impact events and things like that. But we have an additional challenge, okay? Why not, right? Okay, so we have the AM bundle that we characterized and the PL bundle that we characterized. We have to then take that PL bundle, twist it back up, then take the AM bundle, put it back, twist the PL bundle up and twist the AM around the PL, and then put it back in the knee, because that's its state in the knee. And what we have from an MRI is just a blob of ACL. So what we figured out how to do, again, another brilliant student, Ben, he took the blob from the MRI, untwisted it. Okay, so now it's in the state that we would be in before we split the tibia to look at the two tissues. From there, yeah.
So, how would you be like positioned, like in this? Are you like standing up straight, or like sitting in a chair, or like?
Here, whoops. Here we're the MRI was at a certain flexion angle. So the MRI that we have is at somewhere between 15 and 30 degrees flexion. So that's the state at which we captured the images.
The front of the knee facing us?
Good question. No, I think it's this way. And a bunch of the condyles removed here so you could see the ACL. So this part of the condyle would be coming over here in front of us. Okay? Okay, so we're going to computationally take what we have from the MRI, turn it into a geometry that matches our experiments, okay? Get rid of all the stresses, put our constitutive model in that configuration, twist it back up, and then do our simulations. So So we untwist. We use a lot of anatomical data to figure out where are the two entheses of the AM bundle and the PL bundles. We can find them on the tibia. We can find them on the femur. Do some fancy sectioning here to find how we go from the femur to the tibia for the AM bundle and PL bundle, where they are in relation to each other, and put the constitutive models in, twist them back up, and put them in the knee. Okay, and so we've done some work in which we've done impact events on this and gait analysis, and started looking at different, how important is it that we have linearity in the ACL or nonlinearity in the ACL? How important is it that the cartilage is modeled as linear versus nonlinear and homogeneous versus heterogeneous? So we started to explore these things, but until we have material models that are accurate for all of these tissues of the knee, predictive capabilities are somewhat limited. But you can sort of make some kind of, some comparisons. But that's, where the work is going long term, right? To try to, do things like cartilage often has these focal defects in them, and there are different potential clinical interventions that one could do. So by studying these, what happens to the knee joint when you have focal defects in there, and then what happens if you replace it with a plug of cartilage from a certain position, and replace it proud or flush or below the surface level. We can help direct clinical decision making, but again, until we have really good, accurate models for all of these tissues, there's still a lot of question about how predictive we can be. But that's where we would like to go. So to summarize the modeling, so I showed you first a literal model of a bundle, right? Just model the heck out of it, right? That's not useful for a full knee simulation. It's just too computationally intensive, but you can. That's one approach. And you can capture what we see experimentally. But where we're going with this is using the virtual fields method and these different nonlinear anisotropic constitutive models to characterize the tissues and build computational models that can work in full knee simulations. So I'd like to acknowledge funding sources. We worked with Comninou, who's at Colorado, to get some of the initial dual MRI work. Caitlin did the DIC experiments. Ben did a lot of the computational work. Callan is doing the dual MRI. Ryan, shear experiments. John is a postdoc. And Uli, a research scientist. Together they are working on really innovating on how we're doing this whole dual MRI thing. We're getting better resolution, better signal-to-noise ratio, fewer artifacts, and higher loads. And we're really excited about the data we're going to be collecting there. And so that's my story today. Thank you very much for your attention.
One of the challenges for looking at the intelligence, so you got the inside stuff looking like next outside. What would be the challenges like looking at measurements?
Oh, the patellar tendon. Yeah. So the patellar tendon is nicer in a lot of ways. It's flat. It doesn't have any sort of twist in it. It inserts into the bone kind of like this. So it's sort of sitting on top of the femur, in front of the femur and tibia. So it has its own complex insertion site, but it's a nice flat tissue. It tends to be long. We've done a little bit of patellar tendon exploration in the MRI, but our chamber isn't long enough for it because it tends to be longer. But it's in many ways easier than the ACL.
Is the collagen structure any different?
Probably not appreciably. No, it should, again, what we call the patellar tendon is really the patellar ligament, and part of it is actually a tendon, right? So the part that goes bone to bone is actually ligament, but then there's a branch that goes off and inserts into muscle. And so that part that's bone to bone is, again, a ligament. And I think what I've been, what we're hypothesizing is a ligament is a ligament is a ligament, and so they should all have the same material properties, unless there are things we can point to that are structurally different about them, like the local orientation distribution function of the collagen.
Have you considered, so the nice thing about knee ligaments is every specimen you have comes with two, the left and right side. Have you considered doing your uniaxial testing and constitutive modeling on one side, doing your reconstruction to the full structural model, and validating that off the other intact side of the same specimen?
So say that again. Have we done what?
So you have two knees.
Yeah.
Right? And one side, you can certainly do the unraveling and
Oh.
do the individual uniaxial,
Yeah.
digital lens correlation.
Oh.
Come up with your constitutive model, recreate the in situ
Yeah.
organization, and then simulate that condition, but also validate that on the
Other knee, on the contralateral knee. So what we have done is modeled the ACL, developed models for the ACL. So this is early on, with the DIC work only. So we got some constitutive models of the ACL. We then took another ACL intact in its physiological state and the experiment we did was anterior tibial translation. So this is the way the ACL fails, right? Anterior tibial translation. So with the twisted pre-strained ACL, we did that. We used DIC to get the contour pattern, and we simulated that experimentally. So we took our two bundles, put them back together, twisted them around, and then did anterior tibial translation and compared the contours to each other. And we got very good agreement between the two sets of contours, experimentally and computationally. That's as close as we've come to that. And that's, it's pretty good. The challenge is the tissue's twisted. As you're doing this experiment, it's twisting more, so your speckle pattern is leaving in some places, and then unspeckled or tissue that wasn't in your field of view is coming into your field of view. So you had kind of a limited area over the surface that you could actually get to correlate, but it.
Question is the interaction between those two, I would imagine, is not
Yeah, and when you model it computationally, you need some sort of friction boundary condition there, and so things weren't too terribly sensitive to what we chose there in the range we chose. But yeah.
Really enjoyed your talk. I
Thank-
have sort of two questions.
Okay.
The first question is about, I was kind of surprised in the first one when you showed that the hysteresis was really reduced in your new testing method. And I was just curious if you saw strain rate dependencies in that material property curve.
So we've, to date, done just a little bit amount of strain rate dependent response. And we've also done some stress relaxation tests. So yes, there is viscoelasticity, there is strain rate dependence, there is stress relaxation. And you can, from the stress relaxation tests, you can get an idea of how to describe the viscous response. And so with two linear springs and dash pots, you can model the viscoelastic response that we saw. Okay, so it had two time constants of the relaxation, but they were linear, and the nonlinearity came in the elastic part, which you see clearly in the experiments. So that's kind of our viscoelastic ligament model right now. Yeah. Oh, yeah, forgot.
So I just thought the uniaxial testing where you see the sample actually expand was just really exciting and interesting. And so I was curious if you've done any more work to sort of quantify that volume change, if it's really incompressible or if you have
Yeah.
an actual volume.
Yeah, good question. And so we've also, from the dual MRI data that we have so far, we can get volume changes. They're still a little too noisy. And so by refining our whole dual MRI experiment, we're hoping to answer that question. They in general mimicked what we saw with the DIC, but they're very noisy. And so the jury's still out on that. But we're working on it. Yeah, thanks.
Go ahead. Go ahead, Zach. Go ahead. So with the MRI, you can see the local impact to some extent, and you also get displacement fields in the MRI. So I was curious if there's some sort of overlap there. You might have answered the question, we don't have the resolution to test the theory figured out, but the correlation between like local structure and particular local response.
So, good question. Is there a correlation between the local response and the local structure? There are other parameters that one can measure with MRI that speak to that more closely than just the phase angle of the processing protons. And that's this like T2 star parameter. Others have tried to use it to say something about the local organization. Or the local diffusion tensor is something you can also measure, which would tell you something about the local structure too, how anisotropic it is. So they're there, they're accessible in this technique. We haven't explored using them yet, other than just talk about, well, maybe we could. But we haven't. It's there though, it's possible. There's some, I think there's the jury's still out on what this T2 star parameter is really getting at, but we can measure it. We see it change as we dry out a tissue, for instance, in the MRI. So there's the potential, yeah, for sure. Oh, he's been.
Oh, sure. I don't like it.
So I probably have 2 or 3 people questions.
2 or 3.
But short questions. Yeah. When I read your paper 2017, so can you maybe explain it when we go back to video? So you
Video of what?
The video show you like organ level FE model.
This.
Yes. So when I check your paper, so it looks your ACL is a single bundle, right? In that picture.
We've done single bundle and dual bundle ACLs.
So maybe there's some update for this 2007. This is the latest video, right? So is that using a single bundle or two?
We use the same geometry and modeled it as a single bundle and as 2 bundle. And we looked at specifically whether you need to model it as 2 bundles. What does that really change?
Yes. There's some difference, especially the material property.
Right, because they have different properties, and so to what effect does that change the kinematics of the knee and the tissue level deformation, right? And so, yes, they're different, but again, we're sort of speaking to this question of how complicated do you have to get to determine what you want to determine. And some things are highly sensitive to getting more complicated, some are not so much.
The second question is that for your I know for your tissue level, you already validated by your experiment, right? So, but for your component level, I mean, it's organ level, like joint.
Yeah.
Did you have any like validation tests?
So,
different motion or even on the impact loading?
Yeah. So we have we've sort of compared to what other computational models are doing to see whether we're in similar ballparks to them. We've done a little bit of impact loading and capture that impact response, sort of the force history during an impact event. And seen how well our strain levels match what's seen experimentally when we replicate that. The big challenge that I didn't mention yet, what's missing here? I mean, probably you could say, oh, everything's missing, but what's one big thing missing? Muscle. The muscle forces. What are they? When? It's still a big question. When I'm standing right here as an animated human being, what are the muscle forces on my leg? We don't know that answer. Some people seem to think we do, but it's a huge challenge. Yeah. And all of the computational models out there, do similar things. They either ignore the muscle altogether or they try to put muscle forces in there. We do have muscle forces in our simulations, but they're empirical at best. So.
That's really beautiful. So I learned a lot. The question I have is related to the radio weather. So when you stretching your tissue,
Yeah.
you saw some stress sticker, which means that the stress will increase the linear strength. But you were using a molecular model for the circumferential chain, polymer chain to explain that. That was very nice explained. But you also some kind of hysteresis, right? So can you comment on the molecular mechanisms on the dissipation of this?
Well, that's a good question. There's a lot of potential mechanisms in a ligament. So there's fluid in there, right? There's fluid moving around. At some level, these fibrils or fibers are connected to each other via, molecular crosslinks, and there may be sliding going on. And so we haven't explored trying to physiologically model the viscous effects. We've just said, okay, Maxwell, spring and dashpot. But there's a fluid phase, and there were proteoglycans and glycosaminoglycans floating around in there. They can, swell and hold a lot of water, and under deformation, possibly release some of that.
Yeah, but do people see possible bonding between the filaments if you use some kind of biological methods between the needle to segment the size of the needle?
So you have to go to much smaller length scales than what I'm observing at, but some people are trying different techniques, 2-photon techniques, other spectroscopic techniques, to try to see what the viscous effects are there. It's incredibly difficult to image a decarin molecule holding two fibers together that then breaks. It would just nobody's definitively figured out what's going on there between the molecules and fibrils and fibers. Yeah. Yeah. Thank you.
All right, I look at the clock. It's already 60 minutes. This is a great seminar, and you learn a lot, and also great interest, and you ask questions.
Yeah. Thank you. Thanks.
You can talk to Dr. Arruda after the seminar. Let's thank her again.